All right, we're going to get back to pages 1 to 3. These are the notes basically related to exponential growth and decay. And the way we're going to go through this, you can just think always when you're doing these videos, you can always pause and rewind. I know sometimes it seems fast. This might be the second video I show of some of these properties. I think I'm uploading my old notes related to this, but just to make sure that you kind of get the big idea, I'm going to recap this ever so quickly. But it's kind of old news, right? You guys did a lot of exponent rules back in Algebra 1 and Algebra 2, I hope. But the big ones are when you're multiplying same bases, you want to add those exponents together. So it'd be a to the m plus n if you're multiplying base a's together. You add those. And then the other is the division of two exponents. You'd write it as a to the m minus n. Now, I'm going to modify that a little bit because I'm going to introduce you to something that I call exponent battle. So if I give you an example like of a to the third over a to the first or a to the second, I think of the top winning by 1. So what I do is I write the a where the highest power was and how much it wins by is the exponent, and you're done. It helps with more complicated ones, like if I give you another example, so let's cap that one off. If I give you one more, if I say like a to the negative third over a to the negative seventh, sometimes you're like, oh man, which one's bigger? We think of on a number line, bigger is the one further to the right. A negative 3 is further to the right than negative to this negative 7, so it would be bigger. And how much bigger it is it's 4 bigger. So what I do is say, hey, the bigger of these two is the top, which is the a on top, a to the negative third. Negative 3 is further to the right on the number line, hence we kind of think of as a larger number on that scale. How much bigger was it? 4. So that's done, a to the fourth. That's it. And whenever I say write it in the numerator and denominator, if what this method does, the exponent battle, is allows you to write a single letter either in the numerator or the denominator with the appropriate positive power, and then in the other spot you put 1. So if there's nothing left in the numerator or denominator, you don't put 0, you actually put 1 in its place. I'll explain this more when we get to some bigger problems, but that's the exponent battle piece. It is completely related to the rule where you take the same bases divided, you subtract their exponents, but it's an enhancement on that process. Next piece is if we're doing product of powers, so our power over power, right? You want to do a to the m times n. And then if you're doing, we always said don't distribute a power over a plus or minus sign, but you can distribute it over a division or multiplication sign, and you must. So I shouldn't say you must. It's often helpful if you do. So in both of these situations, I'm distributing the power because it's division and multiplication, not addition or subtraction, where that, by the way, is illegal. So this would be a to the m over b to the m. So those quick examples. Negative exponents, there are a lot of times we don't use those. We omit them. We try and find ways to simplify. So if you have a to the negative m, that's the same thing as 1 over a to the m. But I think more importantly is what if you have 1 over a to the negative m, that's like this. What it actually means is you take where that exponent is, where the base to a negative exponent is located, as in, is it in the numerator or is it in the denominator? You move it to the other part of the fraction and you change it to a positive power. So this becomes a to the positive m on top. And remember, there's never nothing left in exponent rules. You always have a 1 if there seems to be nothing left in the numerator denominator. There actually is a 1. Okay, so those are kind of 2 examples for 1. So I want you to know those are 2 separate ones. Let me box those off. It's like this is what's written in your paper. This is me conducting one more example for you. I think, oh wait, never mind. It's right there below us. I forgot. I had it in the note. So just put that in that spot right there. I already had it available to you. The x over y to the negative a is another negative exponent example, and a cool way to deal with that is there's 2 things you can do. You can distribute it to each of these and then respectively move those to the other part of the fraction, denominator to numerator, numerator to denominator. Or, so let's play that actually. Let's try that out. That'd be x to the negative a over y to the negative a, and then because they're both negative exponents, I would move the y to the numerator and make it a positive y to the positive a, and then I would take the exponent up top here that has x to the negative a, I'd move that to the denominator. So you'd switch these respectively to the other part of the fraction. So I take this and it becomes y to the positive a on top and x to the positive a on the bottom. Now if you're kind of seeing the long and the short of it, the other way to interpret this is you can actually just flip the entire fraction. And so this would be a kind of option 2 the or, if you think of a negative exponent as simply something that flips a fraction over entirely, that can be helpful as well. So x over y to the negative a is the same thing as y over x to the positive a. So you flip the whole thing, and that's exactly what we're seeing right here in the example that we already did. If you think of this, if you look to the right, this is the same thing. We would just distribute those a powers over to y and x respectively, like you see right there, and you'd get the same thing. But one way to think of negative exponents outside a larger fraction, like you're seeing here, is to flip the whole fraction, and then it's now y over x to the positive a. So I'm going to get rid of the little highlights so this doesn't look too crammed up with stuff. The zero exponent property, anything to the 0 power is 1. Doesn't matter what it is. And that was where we left off. That was that first video, and it did some more examples. I want to walk through those again in case round 1 wasn't enough, but this is up to date with the more current note packet that we have. So next page, let's flip it over, or next problems. The bottom here are some radical exponent things that are really important. So radical exponents to the 1/2 power is the same thing as square root. 1/3 power is a cube root. If you combine them, what I like to think of is you can turn this into x to the take that back one step. It's x to the second to the 1/3 power is kind of how we're seeing it right now, because we know that power of a power, you multiply those together. This is the same thing as x to the 2/3. Right? If you did power of a power, you would multiply the 2 times the 1/3, which is 2/3. And the reason that's important to recognize, we're going to split fractions up. So when we have more complex fractional exponents, we split it up into a product of 2 different numbers. And there's actually 2 ways we could have done it. I chose to do it the way that you're seeing right now, x squared to the 1/3 power, because that's what we're seeing in our example right now. Oops, I meant to put that forward back on there. But if you take a look at this, this is x squared right there is present, and the 1/3 power that you see right there becomes the cube root that you notice on this side. So you can split any fraction into the product of 2 numbers, one of them being a fraction, one of them being a whole number. The other way that I could have gone about doing it, which wouldn't be as helpful in this situation, is I could have also done x to the 1/3 to the 2nd power. So it depends on what kind of helps you the most. We will split complex fractions into a product of 2 numbers like this, and we'll choose it with some wisdom down the road. So keep an eye out for that. All right, let's get into, let's see, these are the be careful ones, as you might expected. 3x squared, whatever the exponent is sitting next to, in this case a parenthesis, that's what it applies to. It is squaring the whole expression 3x times 3x. You wouldn't, now we can use an exponent rule. We could have gone and distributed that power over the product and made it 3 squared and x squared. That would have been equivalent, but there's an easy mistake to make. Sometimes somebody just does 3 and then just squares the x, but you really have to square both because you are multiplying 3x by 3x. So we could have used the rule, distributing the power over a product. Now down below, here's the one where you cannot distribute the power. Never, ever, ever distribute the power over a plus or a minus. And that's the one you want to keep in mind. We've talked about, putting your nose in the corner if that were to happen. Kind of remind yourself, don't distribute the power over a plus or a minus sign. That's the big no-no in class. And we're seeing it in an official form right now. So here's x plus 3 times x plus 3, FOIL it out, voila. Just reminders, be careful. Simplifying these that happened in the other video, and I believe they match, so I don't think there's any issues with these. I can look back at it if they look different. But I'm going to go on to the next page because I just want to make sure the rules are all fine and dandy. Here are some great simplifying. Here's number 11, and I can use that exponent battle thing that I was talking about. So when you're dealing with simplifying with exponents, you're going to usually see expressions with division or multiplication involved. You want to deal with your numbers first in something like this. So the 5 over 15, that simplifies over to 1/3. I hope that doesn't take much explanation. But I want to talk about the v's. I am going to do battle. Do you notice that the top has a higher power, and it is higher by a 8. 8 is it's because it's 6 on top and -2 on the bottom. The difference between 6 and -2 is 8. So what I'd say is the top wins. So I put the v on top. So you put it in the place of the winner, and it wins by 8. Done. So this ends up being 1/3 v to the 8th. And I actually got into V8 juice over break. It's something that I loved when I was a kid, and I got it out for our kids to see if they try it. One of them liked it. Graham was the only one, really. But I love that stuff, good old V8. The commercials are always like people are always walking sideways until they have their V8 juice in a given day. Yeah, check it out. The next one is number 12. Has a power outside, which means, and all this is multiplied inside, which means I need to distribute that power to every single one of these. You can and often need to distribute a power over a product or a quotient. So this becomes 4 squared, and if an existing power is already there, a power of a power, we need to multiply them. So it's x to the 6th. There's a 5 on the y already, so that's y to the 10th. There's a 2 on the x already, so that's x to the 4th. There's a 4 on the y already, so that's y to the 8th. Any common terms, like the x's and the y's, we can multiply those together. So I'm going to put 16 for 4 squared. Hope that's all right with you. The x's, when you're multiplying x to the 6th times x to the 4th, you would multiply same bases. This is when you add the exponents. So the confusion in this one is when you are doing power of a power, you multiply them. When you are multiplying same bases, you add the exponents. So this is a good example of where to be careful of when do I multiply exponents again and when do I add the exponents again, and be able to distinguish between those two. Multiplying the y's together, they're the same base. I will add their exponents to 18 and done. Is there another way to go about this? Absolutely. I could have from the beginning gone through and combined the x's in the early part of this. So had you seen this and said, hey, could I have made that x to the 5th, and could I have made the y's into y to the 9th? Absolutely. And then distribute the power. And to see that in action, if I take it down here in red, what that would look like is I'd still have 4 squared. I'm sorry, not 4 squared. I'm not distributing yet. Back that up. I'd have 4, and then I'd put the x's together before distributing the power of 2. So it'd be x to the 5th, y to the 9th. And then up top here, I put, still have the y second. I'm doing the combining first, and then I distribute the power. And if I do that, I get 4 squared. I'm doing power over power of these, so it'd be x to the 10th, and it'd be y to the 18th. Notice that's exactly the same thing as what I got before. But what I did is a different route. You can order of exponent rules. There is no order. You just need to apply them carefully. If you want to multiply same bases of x's first and same bases of y's and then distribute the power, great. If you want to distribute the power and then after that combine, that's also okay. There's no order of operations for the exponent rules, but you just need to make sure you apply all of them very carefully, one at a time. 13, another good example of that. So if I bust down here to number 13, deal with the numbers first. 26 over 4. Just simplify, as best you can. They both are divisible by 2, so 13 halves would be reasonable. And then I start lining up variable to variable. I look for x's to match with x's. I only have an x, so I don't have to match it with another. But I do have a pair of y's that are alike. And here's what I'm thinking. This is me in the exponent battle. I always work with this first. If you have a y over another y, or an x over another x, or some matching variables in a division, I'm going to look at the y's right now, and I realize that the bottom y is a power of -2, and on a number line, that's a larger value. So the larger value of -2 versus -3, it's bigger by 1. So I put y where the larger power is, which is the denominator, and give it the exponent of how much it won by, and it won by 1. So it's 2y to the first. This automatically gives me y in the appropriate part of the fraction with a positive exponent, and it's a quick process. The x, on the other hand, I have to deal with. This x to the -1 is in the numerator, and if I want that negative exponent to go away, I need to move it to the denominator as x to the first. This one is done. 13 over 2yx. Let's leave it at that. 14. Now you can do what we mentioned before. Do you want to distribute the power first and then mess with your a's and b's? Or do you want to mess with your a's and b's right now inside the fraction and then distribute the power of 2? It's correct either way you do it. So this particular time, I'm actually going to go about simplifying inside first because I want to do this exponent battle business. I'm kind of enjoying it. So I'm going to go right away to the 3's. I'm going to go below, so it's kind of fun to watch. Now the 3 and the 4 don't simplify, so I'm just going to put them back. But the a's, if you look at them carefully, the bottom is a bigger power, and it is bigger by 6, so it's a to the 6th on the bottom. As in, how much bigger is 3 than -3? The b's, the b to the 5th is bigger, 5 is obviously larger than negative 4. How much larger? 9. So I write b on top, where the higher power of b is located, and by how much is its new exponent. Now I haven't distributed the power of 2 yet, so I will, but I took care of the inside first. I could have distributed the power of 2 early, however I decided to simplify inside first. Now I'm going to distribute the power of 2. And you do distribute powers to all things attached by multiplication and division. So that means the top 3 gets squared. The b to the 9th becomes b to the 18th, because in power over power you multiply. The 4 gets squared. The a to the 6th becomes a to the 12th, because power over power you multiply. And we're essentially done. The only other thing that might be asked of you in a given situation is 3 squared is 9, b to the 18th, and 16, a to the 12th. We'll call it good. Okay, so I got to 14. I'm going to round these off as our first video and then send it out to you. And then the next one, we'll break into, what page 3 we'll start looking into. But this is page 1 and 2, all set to go. E to the 2x, e to the 5x minus 1. This is where a lot of folks get goofed up. Same thing in the next one. You have to be really careful about the rules. The rules say e is the same base. E is a number. So e is somewhere between 2 and 2 is less than, I should put it in there, e, which is less than 3. Okay, it's between 2 and 3. It's 2.71-ish. Okay, that's a good approximation of e. It's a number. So when you're multiplying same bases, which is the same base, you add the exponent. So it becomes e to the 2x plus the 5x minus 1. The rule is if you're multiplying same bases, you add there, write it as a single base, and add the exponents. A little simplifying in there, it's e to the 7x minus 1. Whoops, but you're done. This messes up a lot of folks. E scares people, but it's a number. Just remember it's like pi, it's a number. Number 16, there's numbers being multiplied. 3 and 5 makes 15. The e's are a matching base, so I'm going to write a single e and add their exponents. That's it. Now I can do a little simplifying after that, but it's 15, and then it's e to the, I can combine the negative x and the negative 2x, and I might just call it 5 minus 3x to make it simple. That is good enough. Now, should I go further? Should I do something? I'm not, beyond this, no. The answer is no. That minus 3x, 5 minus 3x, that is not a negative exponent per se that we need to deal with. It's an expression for an exponent, so that would be enough simplification at that point. 17. Deal with your numbers first. 10 and 5, take care of those first, and that makes 2. And once you do that, then you deal with 2 over 1, maybe more specifically. When you're dividing same bases, which is the same base, you subtract the exponents. Now, some of you might say, can I do exponent battle? You can. Do you notice that the top e to the x has a higher power? Because e to the just regular x is 3 bigger than x minus 3, if you want to think of it that way. So if you do that, we're going to get e to the 3rd on top, because the top is bigger by 3. I'm not going to do that just yet, because what I'd rather do for you is I'm going to kind of show you the old rule. I'm going to do both. How about that? But what I will do is if I have division of the same base, like that, I can write it as an e, and then just subtract the exponents. The danger of this is you'd have to use parentheses, because you're subtracting x minus 3, the quantity. And if I do that, I get 2e to the x, and you distribute the negative here, x minus x plus 3. The x's will cancel, and you get 2e to the 3rd. That's option 1. That's kind of using the rule, divide same bases, you subtract the exponents. It works. If, however, you were to do the battle that I mentioned, then you could have just said, all right, this is 2 over 1 for the numbers. The top e wins because x is bigger than x minus 3. So you put e up top. How much bigger is it? It's actually 3 bigger, because the bottom one has a minus 3 with it. So I could have just jumped right to it. It worked. Exponent battle is an awesome, quick route to the same result we got by using the rule for division of exponents more formally. Last one, number 18, and we're going to make my 20-minute goal. This is power of a power outside. If you have a power, you distribute it to all the terms inside. So that means 5 gets the 2x power. E to the negative 3x, that power, whatever power inside already exists, needs to be multiplied to the power you're distributing inside there. So you're going to get, I'm going to write it, negative 3x times 2x. And I'll just write that I'm multiplying them rather than actually multiplying it out just yet. But when you distribute a power to within a product or a quotient, you distribute it to each term, and then whatever power is already there, in this case negative 3x, you multiply by that one you're distributing. I'm going to keep going because now I've got this big string of products. I've got e to the x, and I got 5 to the 2x, and I've got e to the negative 3x times 2x is negative 6x squared. And if you notice, I do things really slowly with exponent rules. There's no rush. There's also multiple routes because the order doesn't matter, but you just have to be careful. I am seeing the same base e's being multiplied, and I know when I multiply those, I need to make one e, and I add their exponents. So I'm going to add x plus negative 6x squared. And there's still a 5 to the 2x going on there, and they're still multiplied. Is there anything else I can do with this? Not really. Plus a negative is minus. Maybe that's the best we could do. But really, we're done with this one. So it'd be e to the x minus 6x squared, 5 to the 2x. Okay, done. That's a lot to take in. Maybe whip back through that, take a look at it again. Try and redo them on your own is always a good practice, even though we've already tackled them. And let me know how it goes. Take care.